Welcome to Thermal Engineering Concept and Principle. This is Professor Ali Tarra. What do you know about vertical heat exchangers and their philosophy of operation with geothermal heat pumps? We mean here the operation of the borehole geothermal heat exchanger. To know that, come with me to go through details of the present episode. Welcome, my friends and colleagues, to introduce the aspect of thermal design for the boreholes in a geothermal heat pump. In this episode, I will introduce the characteristic of a borehole heat exchanger and its installation in the ground, accompanied by its main components to construct a heat exchanger that is called borehole type, which is a vertical heat exchanger. In this part, I will cover the construction of the heat pump itself and the borehole and how can we estimate the depth of the U-tube in the ground, which is related to the properties of the geological aspect for the ground and the thermal properties of the grout or filling that is surrounding the U-tube in the ground. Thank you for continuous support and let us keep on this series of videos in this field, which is the renewable energy source called geothermal energy. The objectives of the present episode cover the geothermal heat pump components. The main components, of course, I will pass through. And then we have the direct contact geothermal heat pump, which refers to the contact between the heat exchanger, which handles the circulated fluid in the heat pump and the ground. Then we will go through the estimation of the depth for this heat exchanger, which is in effect, we are calculating the surface area of the heat exchanger to achieve a certain heat or cool load. And finally, we will approach, as usual, the closure for the present episode. In this system, we have the heating mode, where Earth works as an energy source to the fluid which passes through the borehole in the blue direction, which extracts energy from the ground and then return back to a heat exchanger
which is a part of the heating pump, then this fluid will give energy to another circulated fluid, which we have explained in the previous slide, and then that will provide energy to space. In that way, we have extracted energy from Earth and transferred to the, for example, domestic use in this example, then heat can be transferred from ground to the utility. In this case, we have the utility as heating for um, house or maybe in a restaurant or other applications. So this is the heating mode, how the heating mode operates. Here we have a vertical heat exchanger, which is called borehole heat exchanger, that is installed vertically inside Earth. It is composed of uh, U-tube, and the U-tube is installed inside a bore surrounded by grout material, and this grout material should be conductive material to facilitate heat transfer and conduction between the soil, the external part as shown in this figure, and the tube itself. So in that sense, we are uh, extracting energy from the soil, which represents the earth structure, conducted to the grout, through the grout material, to the tube surface, all of that in conduction, and then by convection to the fluid which is passed inside that U-tube, and it could be water, shown in the right hand side photo, water inlet and water outlet. Water inlet representing the blue one, and the outlet is the green one. So hot fluid or hot water, we will get it from that bore hole, and can be used for heating purposes. Almost similar system can be used for cooling system as well.
Here we have the condenser, which represents the fourth main part of the heat pump itself. So we have the underground heat exchanger, the borehole, represents the condenser, and the other parts which compose of evaporator, compressor, and expansion valve, represented by the other side, which is out of the ground. Then what we have, the ground part represents a condenser. Here we have the refrigerant vapor, which is circulated in the heat pump, passes through the inlet part of the heat exchanger through the red line, and then it reject energy to the ground, of course, through the filling or the grout to the ground, and then returns as a liquid refrigerant to complete the closed circuit of the heat pump. Again, this is a DX geothermal condenser because we didn't need an intermediate fluid to transfer energy to the ground, because the main principal part, which represents the fluid that is circulated in the heat pump, is the liquid which passes through the heat exchanger. How to estimate the borehole depth? Let us consider a model where we have a U-tube as shown in figure A is transformed to single offset tube that is called eccentric arrangement as shown in figure B. Then we would like to have a transformation of the offset tube to an a tube that is concentric as shown in figure C. Here we will depend on the derivative which should be followed to obtain an arrangement to show that the resistance of an offset tube R sub off equal to 1 divided by S sub F K sub G, where K sub G refers to the Groot thermal conductivity, and S sub F is presenting the shape factor of an eccentric tube that is shown in figure B. We have also a concentric tube where it has an equivalent diameter, and this resistance is referred to R sub E equal to 1 divided by S sub E K sub D. And we have S sub E, the shape factor of a concentric tube in a cylinder. It is represented by S sub E equal to 2 pi L divided by natural logarithm of D sub B, which refers to the bore diameter, divided by D. For a constant thermal resistance of the offset and the concentric equivalent tube, we will get that the shape factor is the equal, and that will lead to D equivalent in the term of D sub B divided by x plus square root of x squared minus 1 as shown in equation number 6. In this equation we have x is presented in terms of borehole diameter, tube diameter, and the tube spacing distance as shown in equation number 7. The derivative for this model is presented in a reference as shown here, and it will be the first of references in a list that will be included in the description box below this video. Let's examine the model which has been already established in this seminar. Let us consider a ground heat exchanger which represents a condenser and a heat pump with following conditions: that we have Freon 410A is circulated in the heat pump with a condensation heat transfer coefficient of 3000 watt per meter square degree centigrade, and it will be used as a typical reference value in the analysis. And we will use a copper U-tube where both legs have the same diameter as shown with in the table for the respective dimensions of these tubes. 3 different geometries with the ratio of diameter to thickness, outside diameter, SP represents the distance between the centers of the legs of the U-tube. D sub B represents the borehole diameter, and the other dimensions represents the ratios. Then we have WF equal tube wall factor, defined as D naught divided by T, and we have T equal to tube wall thickness. The objective is to predict the depth of this heat exchanger. Or filling thermal resistance comparison. Usually, the equivalent diameter of a U-tube is presented in the form of beta times D naught, which has been used by many investigators to represent the U-tube in the form of equivalent diameter. We have the borehole thermal resistance equal to a grout resistance plus tube or pipe resistance. And the pipe resistance, we know that it is composed of two components. The first represents the convection, and here we have the condensation of freon inside the tube, plus the conduction part through the tube wall. And to get the total resistance, we have to add R ground to the borehole resistance, and then to get the heat loading, which is represented in terms of watt per meter, it is equal to delta T mean divided by R total. And then we may get the borehole depth equal to Q condensation, which represents the total load of condensation of the heat exchanger, divided by small letter q, the heat loading, and then the result will be in meter. The condensation heat transfer rate is calculated from a mass flow rate of freon, R 410 times A, times the latent heat. And here we have a detailed description of the dimensions which have been used and to calculate different parameters, and the final column will include the grout or filling resistance. It has been used for different investigators, both et al., present work, Gu and O'Neill, and Sharkawi et al. And all of these dimensions may be used in our correlation. If we have a look at beta, which is represented by equation 8, both et al. Give beta is constant. Present work and the work of Gu and O'Neill give the value of beta is function of the geometry of the U-tube and the borehole dimensions. Therefore, you will get it in it varies from one design to another. And the filling resistance is clear that the both et al. And our present work almost are similar, but it depends on the dimensions of the tube and the borehole, as shown in our present work, and the minimum value is produced by Sharkawi for all of the geometries. And here we mean the geometries that for different values of D naught and SP and DB. For three designs, we have the lower values for Sharkawi when compared with other results. To get the Groot and total specific thermal resistance, here we have a presentation for the thermal resistance or the specific thermal resistance of a Groot for two designs, the WF 14.29 and WF equals 17.86. All of these correlations have shown that they have the same trend, and the value of the resistance uh, showing a declination with increasing of the thermal conductivity of the Groot. And uh, the present model and GU, in fact, because they depend on the design, so they have a good variation depending on the design, and the highest value was predicted by Boss et al. And the lower value by Sharkawi for both designs. And for the 17.86, the three correlations, the present correlation, Raymond, and Gu and O'Neill, they have almost similar values, and they occupy midway between the higher and lower values of the specific or Groot thermal resistance as predicted by Bose and Sharkal. We have also the specific total for both designs by adding the ground resistance equal to 0.053 meter Kelvin per watt. And again, we have a similar trend for the results, and the maximum is predicted by Bose and the minimum predicted by Cherkawi. And of course, these values will be used, I mean, the total values will be used to predict the uh, heat loading of the heat exchanger, and then we may calculate the depth of the um, heat exchanger. Heat loading estimation, because we need to calculate this parameter in order to find the depth of the borehole. Uh, if we depend our estimation on the case where we have a mean temperature difference between the soil and the condensation inside the tube to be delta T mean equal 14 degrees Celsius, we may calculate the heat load. And for the case where we have 14.29, it has been calculated for different values of thermal conductivity, and is the same for 17.86. It has been calculated for different thermal conductivities. In both figures, we may find that Sharkawi et al. Predicted the highest heat loading because it has the lowest total thermal resistance, and the minimum was predicted by Bose et al. For both cases because we have here the higher heat thermal resistance. Therefore, the value of uh, heat load depend directly on the value of the total resistance. And again, all these correlations show the same behavior, and the heat load increases as the thermal conductivity increase. Uh, if we have a look at the cases where we have WF equals 17.86, we may find that three correlations occupy almost the same values and the same behavior uh, for the present web, Raymond and Go and O'Neill. And these values were closer to the Bose et al. And really is surprisingly that these values may produce high values. I mean, for the Sharqawi, may the value approach 130 watt per meter at thermal conductivity of 1.9 and comes down to the case around 75 or 76 watt per meter for the case where we have a thermal conductivity 0.73. And similarly, when we are talking about 14.29, almost 110 at highest value, comes down to around 60 for the lower value or examined value of thermal conductivity. All of these um, correlations predict the heat load, but we have to be accurate when we select the correlation which will be used to estimate the heat exchanger design and the depth of the borehole. My friends and colleagues, we have arrived to the final part of this video, which is related to the closure. We passed through the geothermal heat pump components, the underground part, which represents the borehole, and the other parts, which are on-ground parts, which includes compressor, expansion valve, and either the evaporator or the condenser for the direct geothermal borehole, where we have the fluid passes through the tube, the U-tube, and is the same fluid which is circulated in the heat pump itself. That's what we call the direct contact geothermal heat pump. And I used one of my published correlations to predict the depth of the single U-tube, and it was compared with other published correlations for specific conditions of the heat load and the physical dimensions of the borehole. There are some valuable references you may find in the link in the description box for some references which are either used in this episode or in you may increase your knowledge about geothermal energy with the others. And usually I put the reference which has been discussed in this episode as the first reference in the list. If you feel that the information and the thermal design is useful to you and others, please subscribe to the channel and share it with your friends, and we hope can achieve the main goals of our for the creation of our channel. Bye-bye.